afternoon. It's a big honor for me to be here. I apologize that I can't speak in Chinese, but I want to follow up right where Academician May and Professor Jin actually ended. Academician May said that the GCC is one organization that connects us humans, and I want to be understood as part of that connection. So I want to be understood as an ambassador being here and helping us to connect. Today I'm going to talk about the age of computation. And this consortium is called the Global Computing Consortium. So it is the Computation Consortium. But I want to make the argument that this computation is actually going to be the fundamental resource of humanity going forward and hopefully to connect. But to make this argument, I want to start very early on in human history. So I want to start 2 million years ago. Actually 2 million years ago, even here in China, where we look at how humans were driven. What was driving humanity at the time? We started with the Stone Age, we moved through the Bronze Age, we moved through the Iron Age. So we were all discovering new materials. You can all see where this was going, because today we're in the Silicon Age. But before that, we used manufacturing, like Roman technology, that's now Europe-centric, but similar things happened here, medieval technology, Renaissance, and the Industrial Revolution. And one interesting thing happened at the end of the Industrial Revolution. Human physical strength became irrelevant. Very frail humans can now steer multi-million-ton ships, or fly planes, or use other kinds of machinery. So now we continue working forward as humans. The atomic age, the space age, digital revolution when I was born. We connected all of these computers in the information age. And many people believe that we are now in the data age, driven by the available data. One question we could ask, actually, is when will human creativity and intelligence become irrelevant? Right? When will we all be amended by a higher power in some sense? And this is something I want to allude a little bit, but I'll leave that question up to you. So the academicians are going to answer that later. But I want to argue that the point that we are at the data age, because I believe we are beyond the data age. In fact, we are at the age of computation. And let me elaborate on this. So many of you have heard about this company. And this is the most valuable company in history today. Well, the most valuable company is the East Indian company, but today it was a $5 trillion company just briefly before the stock market crashed the last days. So it is the largest company today still. This company makes no data storage devices. They only make compute devices. So the most valuable companies are making compute devices. Furthermore, Sam Altman, one of the OpenAI founders and CEO, he says that OpenAI, and that was about a year ago, more than a year ago, generates 100 billion tokens per day, 100 billion words per day. Humans speak only 1,000 times more. So now imagine that was about a year ago, more than a year ago. What's happening now? Many people believe we are running out of data. So in some sense, we are already at the point where machines generate more content than humans generate. Many people see this negatively. I want to see this positively. I think there's a huge opportunity because what we can do now is we can have these machines argue with themselves. We can have these machines invoke in loop like we humans do. We can build thinking machines that have an argument among each other that actually go forward and discover new things. And I want to motivate a little bit how you could do this. One of our research contributions in this area is Graph of Thoughts, which is an extension of Chain of Thoughts, which probably most of you know. And I want to elaborate a little bit more on this. But my central comment here for the GCC is that computation is the new oil. And now the wonderful news is we pretty much have oil everywhere. I'm from Switzerland, but we also have that oil in China, we have that oil in Abu Dhabi, we have that oil on every part of the planet, if we just invest into it. We have actually used this oil in China to build our own language model. Like many have built we've used that oil in Switzerland to build our own open language model. Many have built a similar language model here in China, actually the most competitive ones. Like the release yesterday of Kimi K2T, a very, very impressive milestone. And I have not updated my slides yet since yesterday because it was technically not possible. But believe me, the world is moving very fast. Essentially, the industry is exploding. What does that mean? Well, back in 2019, Microsoft first pledged $1 billion. That was one of the first public announcements in big, large-scale AI. Furthermore, there was a comic on this. But then Google was making announcements. Facebook, Tesla, a car company builds AI. You could actually see the statistics of how many GPUs were sold. And you can see that in 2023, 300,000 GPUs were sold just to Microsoft and Meta alone. In 2024, just Microsoft alone, about 400,000 GPUs. You can also see several Chinese companies here, number 2 and number 3, immediately being there in the largest GPU market. So the world is cooking. Today, people are investing even more money, $80 billion, $500 billion announced. So huge investments go into this. But what is this? What is this AI? I want to just briefly elaborate what it is. And it's one of the simplest computations you can actually phrase. Because all you do is you take text off the internet, and there's a lot of text on the internet. You run it through a parameterizable model, which is a very simple computational structure. So this structure has about 12 operators. Any student can implement this in about a week, maybe a month if the student is slow, but it's really easy to implement. And then what we do, this structure predicts the probability distribution of the next word. What we do is we, of course, know which word we removed. You can read the text. And then we update that computational structure with many, many parameters over and over again to reproduce that text more faithfully. That's it. That's the magic of LLMs. That is what's driving the field of AI today. Think about this, a very simple computational structure. Now, you just do this at extreme scale. So one of the largest models, actually the DeepSeek model, but again, yesterday a 1 trillion parameter model was released, so it's not up to date anymore as of yesterday, but was trained with nearly 15 trillion words or tokens. DeepSeek v3 has about 671 billion parameters, about 37 million of those are active at any given moment. And then it takes weeks to train this model on the largest compute infrastructure that you have today. So now, how do we actually make these models feasible? How do we make these models fast? And this is something I want to elaborate a little bit on. The time does not allow me to go into great detail. In my research group, we have discovered many, many of these topics. For example, quantization. What does quantization do? Quantization actually takes every parameter. I mentioned there are trillion parameters, or 600 billion parameters, many, many parameters. And we compress the size of these parameters. We've just heard about the high float 8 format and the high float 4 format. These are smaller, smaller data types. We use less and less bits to represent the same information. And that is very fundamental, because then we can make the models smaller. Furthermore, sparsification. Pretty much all of us have heard about mixture of experts these days. Mixture of experts is nothing but a form of sparsification, and we are driving that towards the extreme. These models are up to 99% sparse, meaning that only 1% of the parameters are actually used to generate a single token. A very fundamental work that we have started back in 2019, actually, and that has led to a lot of success. Mixture of experts is probably the biggest one that is not attributed to us, but it is in that framework of sparsity. And then at the end, what do you need? You need to build a large machine to make this work. And the large machine, a large supercomputer, is mainly defined by the network. A large supercomputer is nothing but a bunch of compute devices connected by a good, cheap, reliable, many call it smart network. Okay, so I've just given you an overview of how you could improve performance by 1000x. I didn't give you any details, I just gave you keywords. If you want to hear details, you can actually watch me talk about this on YouTube. It's a 1-hour video, so I don't have enough time now. But if you want to, you can easily access it and look at it. But now, what happened in the LLM area? We basically went from transformers to the BERT model. Many of us know this. To the GPT-2 model. That was when OpenAI came in. To the GPT-3 model. That was when OpenAI came out, basically, and said, we have a competitive product now. GPT-3 was the first one. And then, I would call this the era of model size scaling. So we're in the age of computation, and we kept scaling the models to larger and larger and larger models. You could argue that's still going on, but in fact, it's not really going on anymore. Because what happened is that ChatGPT language models came out as a product. And now what you realize, if you want to productize an LLM that is an extremely large model where you have to go through billions, if not trillions of parameters, it's extremely expensive. So what people did then, they competed in an open market, and this is where also DeepSeek comes in. And then the era of data scaling started. So model size was not a primary concern. The concern was actually run more data, run more tokens through the model. And there was a big game changer. But now what happened then? And this is even more important for the age of computation, even more important for the argument that computation is the new oil. So what happened then is that we essentially ran out of data. So very famous scientist, one of the co-founders of OpenAI, Ilya Sutskever, says, pre-training as we know it will unquestionably end because we have only one internet, which is very obvious, because I already mentioned there is more automatically generated text than we have humans generating text today. A friend of mine, David Silver, who also won the prize in computing, says human data is the fossil fuel of AI, which it very much is. We could not exist as a humanity as we are today without fossil fuel. We have used fossil fuel, but we are running out of fossil fuel today. So we need a new fuel. And that's where it gets interesting. So how do we continue the scaling of LLMs? Many of you have seen this diagram, and if you haven't seen it, let me quickly explain it. On the x-axis, you see all kinds of different exams that humans take in the United States. The middle line is the performance of the average human. Right? So that's Mr. Joe, the average human, or Mr. Wang here maybe. And Mr. Joe, you can see, performs, and this is the performance, the higher the better. And you can already see language models, GPT-4 or GPT 3.5, perform better than the average humans in the majority of the tasks. But what is wrong with this? What's wrong with this? These are all knowledge tasks. These are literally looking up knowledge. They're not reasoning. So what is wrong with the reasoning thing? Well, they don't know how to reason. But there is one interesting effect that we can see, a deep discovery, that if you replace basic input-output with, for example, this task, sort the numbers, and it happens that this is not general knowledge. You won't find the sequence of numbers in the internet. But if you now tell the model, this is how you sort numbers, and now apply it to my sequence, then something interesting happens. That's called chain of thought. Many of you know this. Again, I just want to summarize it for everybody. And the idea is that the model actually itself kind of understands and reasons about what to do. This has been continued with multiple chain of thoughts, tree of thoughts, and graph of thoughts, which my research group eventually contributed to the field. So just a little bit more of a detour how this works in practice. I want to go back to 2016. In 2016, Lee Sedol, the world champion in Go, a game that is very popular here in Asia. It's a game that is super, super simple. Most of you know the rules. It's super simple to explain. You can explain it to a small child, but it's extremely hard to play. You need a lot of thinking, a lot of strategy to play that game. So the 18 times world champion was beaten by a machine. So that means a machine can reason somehow better than humans can, at least in that one example. How did it do it? Well, it applied reinforcement learning. Reinforcement learning, how does it work? We have a state, a starting state of the board. We run a so-called policy function that gives us a new possible move, which puts us into a new state, S10, and then we run this m times to sample m different possible new states. Then we invoke a value function, and this value function will actually give us the probability of winning from that new state. And then you take the highest probability, and you do the thing again. And you do it over and over again. You may need to backtrack. You do it over and over again. At the end, the machine was applying this very simple algorithm to beat the best human player. How did the machine learn the policy function and the value function? Well, it was a deep neural network. That was the breakthrough. At the end, that led to multiple Nobel Prizes, to actually at least one Nobel Prize, and the Turing Award. So the techniques used are Monte Carlo tree search and many other details that I don't have time to go into. But now imagine that same idea applied to text. The language model now starts talking to itself. It gets the task, sort the numbers. But now instead of looking at a new state, these states are instructions that it gives itself. For example, look up quicksort. A good idea. Numbers are blue, bad idea. Right? And you keep doing the self-play. But this time you don't play with states on a board. You play with words, you play with your thoughts. And now imagine the possibilities that this opens, because the language models are already the best databases, and now you put them in a loop to do the best reasoning, superhuman reasoning. And we could go into more detail, but I'm slowly running out of time. But what you do at the end is that these models themselves argue with themselves. So we are combining superhuman strategy play, a technique that has beaten the best human in a game like Go, which is one of the hardest games strategy-wise that we know as humanity, together with superhuman knowledge, which we already know is that the LLM is pretty much better than any of us in this room, maybe even better than everybody combined in this room in knowledge questions. And that is going to be a big game changer. And this is what started the era of reasoning scaling. This started at the end of last year. The nice thing is we are not done yet. If I had some more time, I would make you do this quiz. It's a very simple quiz. You would take about 30 seconds to solve it. I don't have enough time to explain it. But you would solve that quiz still better than the AI system could. So we are not done yet. But we are now in the middle of the era of reasoning scaling. But what does this mean? We are actually compute bound. We really need to build these computing machines to help us to perform this computation, to make the models argue with themselves, to make the models reason. What are the principles for this? I've already mentioned those. Sparsification and quantization. Again, what we want to do is we want to make sure that we don't need to look at all the parameters. Every time I'm going through my brain, I'm not lighting up all my neurons. In fact, I'm only lighting up about 20% of my neurons in my brain. If I'm lighting up more, even 25%, I would be having a seizure and I would lie on the floor. So that's not a good thing if you're too dense. Quantization is the other method. Again, reduce the number of parameters. My brain runs on 4.2 bits. Why does it run on 4.2 bits? Because you can measure that every neuron in a human brain can actually only differentiate about 24 voltage levels. So that is about 4.2 bits. So how do we now build these systems of the next generation? How do we build machines that can reason and that can be knowledge machines? Well, we need cheaper compute. So here's an example, a Microsoft Maya 100 chip, a Blackwell chip. I could put the Huawei Ascend here as well, but the principles are always the same. We have better data types, like we just heard about high float. We use sparsity, that is inherent in a mixture of experts, for example, or other forms of sparsity are possible, and we implement those on a spatial device. But that's not all. That's the chip. What we also need is cheaper systems. We need to integrate these chips into larger systems. How do we do that? Well, we build a network. We build network switches. And here I want to talk about a standard. At the end, we are at a standards organization here. I want to mention a standard that's very dear to my heart, Ultra Ethernet. And the principles are high bandwidth, reliability, and cost, low cost. At some point, the networks converge, and every data center will be a supercomputer because the network has to be extremely powerful to solve these computational tasks. And you could look at this paper if you're interested that today's networking technologies that are based on Ethernet are not good enough to fulfill that task. They're not good enough to scale to the next generation interconnects. You just have to trust me. If you don't trust me, read this paper and you will understand what the problems are. This is why we founded the Ultra Ethernet Consortium, and many Chinese companies are part of that. So it's, again, connecting all of us, very much like the GCC does, and actually published a nice paper. So today we have 10 steering companies, 26 general members, 54 contributor members. This is how it looks like. It's how it looks like when you discuss a standard, very much like many of us do. By the way, I'm not on this picture because I'm taking the picture, because I'm the chair currently of that consortium, and there's my wonderful co-chair there, Karen, on the very right, who's helping to run the show. Unfortunately, I don't have enough time in this talk to talk about all of this, because Ultra Ethernet is quite a complex technology, but believe me, this is the network technology of the future. It would be great to engage on that technology. So if you're wondering about all the technical details of this technology, I recommend you reading this paper. This is on arXiv today, and you can understand all the details of networking, of how do you make Ethernet AI ready? How do you take a network technology that has been around for nearly 40 years? Just recently, the Turing Award, the highest award in computer science, was given for the invention of that network technology, to a now friend of mine. If you rather want to look at a talk and don't want to read a paper, I've given a 2-hour talk on Ultra Ethernet. Again, not enough to discuss here, but you can also find that talk online. So with that, I would like to close my discussion, and would also want to give you a little bit of a further outlook in case you want to hear the full story. So I only had 20 minutes here, but the full story of how computation can develop, how the 1000x actually gets into place, is also online as a YouTube video that you could watch me give the full briefing. But again, it's about 1 hour in length. So with that, I would like to close, and thank you very much.